I feel like we're down a bunch of people. I'll give them another minute to. Okay, so last time we proved this theorem. Relating the vertex connectivity, the edge connectivity, and the minimum vertex degree. So it said that kappa of G is less than or equal to kappa prime of G, which is less than or equal to delta of G. So yeah, this is vertex connectivity. This is edge connectivity. And this is minimum vertex degree. So I wanted to take a look at some examples of situations in which these are equalities or inequalities and like what conditions can cause that. So for some examples. So I'm going to ask you all to provide examples of the following situations. So one is when kappa of G is equal to delta of G. Another one is when kappa prime of G is equal to delta of G. And then we'll also look at kappa prime of G strictly less than delta of G. So maybe if you can think of like a condition or something for this one. And then lastly, let's try and write an example of a graph where kappa of G is equal to 1. So they're all unequal and equal to these values. So kappa prime of G is 2 and delta of G is 3. So go ahead and take a few minutes to think through what some examples of these might be, and then we'll discuss. Just make a little room. Okay, what examples do we have? So for this first case, when the vertex connectivity equals the minimum vertex degree. Yeah. Yeah, so complete graphs. Any other examples? Cycles. Um, yeah, because deleting two vertices would disconnect it, and also the degree of everybody is two. Yeah. Other examples? I had two others written down. One was complete bipartite. And then also the Harari graphs from last time, which was like, I don't know how we denoted that. What were the two numbers called? KN. Okay, good. And then what about when kappa prime is equal to delta G? So we have like automatically all these same examples just by the theorem. Did anyone have any other examples? Or like, can we think of one where kappa is strictly less than kappa prime is equal to delta? Maybe we can cook one up. So like, let's say we have this vertex and let's try and make that one be the vertex that has minimal degree. And then this is going to be our minimal edge cut. So then how do we force? Can we make it possible? I don't know. Yeah. Yeah, looks good. Okay, yeah. So this is the example also for this case, right? So we can disconnect the graph by deleting that one vertex. If we delete, there are pairs of edges that we can delete, but no single edge that disconnects it. And then the minimum degree is 2. Oh, okay, so this is not an example for this one. We need the minimum degree to be 3. Okay, but this is an example for this. Okay, what about examples where kappa prime is strictly less than delta? So I said this was true if and only if no minimum edge cut isolates a vertex. So why is that true? Yeah,
If no minimum edge cut isolates a vertex, that means that any minimum edge cut is gonna be something other than just deleting all edges around the vertex.
Mhm.
Which means it will, since it's not that and it is minimum, it's gonna have to be like less than the degree of the minimum vertex.
Yeah, because like an edge cut that isolates a vertex will always disconnect the graph, right? So if it's not the case that a minimum edge cut does that, then there has to be something smaller. Yeah. And what about the reverse direction?
Um, Well, again, if one of the minimum edge cuts isolates a vertex, then that's just like, since it's minimum, you take the minimum degree, and that would just be delta G.
Yeah.
As your like number of edges to leave.
Yeah, sounds good. Okay, and then did anyone come up with this last example? One where the minimum degree is 3. Kappa prime of G is 2 and kappa of G is equal to 1. Yeah.
You create like two complete graphs with 4 vertices, and then like connect them each from 2 vertices that share vertex between the two. I think that.
So, okay, so then we're going to connect them like this. Is that, yeah. Okay, yeah. So we have kappa of G is 1 because we can delete this vertex. Kappa prime of G is 2 by deleting either one of these, and then the minimum vertex degree is 3. Nice. Can you generalize this construction to make any set of numbers that you?
With like, I mean, I guess not any, but within like certain bounds.
Yeah, so like what could we like? Okay, so if we want our minimum degree to be 3, okay, yeah, so what would we need to do? Whatever kappa of G is meant to be, like I guess put that many vertices in the middle. And then whatever delta is gonna be, we're gonna take complete graphs that have that degree. It's like not clear to me how to force the kappa prime. Okay, so maybe this is like a question for further investigation. Can we generalize? To get any kappa prime, and delta. Okay, so we'll table that for now, but if anyone comes up with something, let me know. Okay, so I'm gonna show you now a condition. So like there's a lot of conditions that imply like equality here, for example. So I'll give you one example of one of these theorems. So this says if G is 3 regular, then that forces kappa of G to equal kappa prime of G. Okay, so let's prove this. So let's let S be a minimal vertex cut. So by the theorem, we automatically have kappa of G is less than or equal to kappa prime of G. So we know so um we want to show that kappa prime of G is less than or equal to kappa of G. So then to do that, what I'll do is just exhibit an edge cut of size S. So to do this, we exhibit an edge cut of size S. Okay, so why? Because kappa prime of G is the minimum possible size of an edge cut. So if I show you an edge cut of size S, then that implies that kappa prime of G has to be less than or equal to S. Does that make sense? Other questions? Yeah. So S is our minimal vertex cut of G. So the number of elements of S is kappa of G. That's all right. Okay, are there other questions? Okay, so we know since S is a minimal vertex cut, G minus S is disconnected. So I'm gonna let H1 and H2 be two components of G minus S. Okay, and then I'm gonna claim that each V in S has some neighbor in H1 and in H2. Okay, so why is that true? Yeah,
Otherwise you wouldn't have to include it in the vertex cut.
yeah. So this is because our vertex cut was minimal. This is by minimality. Yeah. Okay, and then since G is 3 regular, so this vertex only has 3 edges coming out of it. So it can't have 2 edges to both H1 and H2. Okay, so now I'm gonna try to make my my edge cut. So for each V in S, I'm gonna delete one edge, and that's gonna be the edge that goes to either H1 or H2 such that V only has one neighbor in that H. So for each V in S, I'm going to delete the edge from V to a member of H1 or H2 such that V only has one neighbor in that H sub I. Okay, so maybe now a picture would be useful. So we have like, here's our set S, which I'll draw in the middle. And then we have H1 over here and H2 over here. I don't know why I put H1 on the right. Okay, so then for each of these vertices, the graph is 3 regular. So I could have one edge, for example, going that way, 2 edges going that way, or I could have, this is basically the 3 situations. Like, so we know it has one edge in both. So then the options for the third edge are 2 to the right, 2 to the left, or staying within S. So this is like the 3 possibilities for how an edge, I guess I didn't say what this vertex is. Okay, so it looks like that. Okay, does that make sense? So this is like how our picture is looking. So for each of these vertices, I want to delete one edge, and I'm going to pick just an edge such that there's only one edge from V to that H sub I. So for example, I would not pick one of these 2 edges. I would take this one. So I can delete that. I can delete that. And then for each of the 2 vertices in the middle, I have options. So could, for example, do like this. Okay, so this is how many edges do we have? Well, we deleted one edge for every vertex in S. So we have
This graph not still connected.
it is right now, yeah. But I mean, yeah, so we're about to argue that like there's just a way to pick these in a better way. Yeah. So this is S many edges. And what does this accomplish? We've broken all possible paths from H1 to H2, except in potentially in these cases where you can enter via some edge, go to another vertex in S, and then exit via that edge, right? So we kind of like picked the edges for this case. We may have done this badly. So in that case, we need to just make the same choice. So let's say, so what should I write? If there is an edge VW between vertices V and W in S, then for both, I should just pick the edge that goes to one of the H's. So I'll just pick H1. Okay, so then instead of making the choice that I did in this picture, so this was like a bad decision. And I should instead just pick the one that goes to H1. Does that make sense? Okay, so now my claim is that these are disconnected. Or so that there's no so after deleting this choice of edges, from my graph G, there are no paths from H1 to H2. Okay, so maybe you should just like say why. So let's say we're starting off in H1 and we want to travel to H2. The only times when I have an edge exiting H1 is when I have a vertex in S that has two edges to H1 and one to H2. So I could exit H1 via one of those edges. Now I'm in S, but that vertex, the graph is 3 regular. It has two edges to H1 and we deleted the one that went to H2. So now there's no way for me to travel between H1 and H2. Does that make sense? So, so that means that, G minus these edges, which I didn't give a name to the set of edges, is disconnected. So that means that, so just like zooming back out, we picked out S many edges that disconnected the graph. So that means that kappa prime of G is less than or equal to the size of S, but the size of S was equal to kappa of G. And that was like the second equality that we wanted to prove. So then we have that kappa prime of G is equal to kappa of G as desired. Are there questions about the proof? It's all good. Okay, so for the rest of today, we're going to talk about two connected graphs. This is vertex connectivity. So this is like whenever you can, there is a way to delete two vertices and that disconnects the graph. So G, this is just like reiterating information we already know. G is two connected if there are two vertices I can delete and it disconnects the graph. Okay, so we have a theorem of a bunch of equivalent conditions for a graph being two connected. So I'm gonna start by stating the theorem and then we'll go through and prove the various parts of the theorem. So let's let G be a graph with at least 3 vertices. Then the following are equivalent. The first is that G is two connected. Second is that G is connected and has no cut vertex. So this, okay, so I want to go back to this. So this statement is not quite right, right? So what do I need to like change to fix it? So I guess like, what is this saying? This is saying that the connectivity of G is exactly 2. But like, if a graph has connectivity 3, then it also counts as being 2 connected. So what? Yeah, so let's like amend this. Yeah. Yeah. So, okay, so we're 2 connected if, I guess, a minimum disconnecting set of vertices has size at least 2. Okay. Are we good now? Because so that would, yeah, so this is just like the way that we set up the definitions is like, so exactly 2 would just mean like kappa of G is equal to 2. But you're 2 connected if kappa of G is greater than or equal to 2. Yeah. Maybe that's like the easiest way to phrase this. Okay, so let's proceed. So, okay, so then the third condition, is this is gonna involve like a word that we haven't introduced yet. So it says for all X and Y in G, or sorry, in V of G, there are internally disjoint XY paths. So what that means is that there are 2 paths from X to Y that don't share any internal vertices. Yeah, okay, so that's the next condition. So okay, so a couple of these are like, I think obviously equivalent, like these 2, and then the fourth one that I'm gonna write is like obviously related to 4. So, or is obviously related to 3. So for all X, Y in V of G, there's a cycle through X and Y. So, yeah, so how do we get the cycle from the internally disjoint paths? If you have the internally disjoint paths, then you just union them together and that gives you a cycle. And then conversely, if you have a cycle, then the two parts give you internally disjoint paths. Okay, so then the last one is that G has what's called an ear decomposition. So I'll say what that is later. So just quickly, okay, so we talked about why 3 and 4 are equivalent. Are you all convinced of this? Yeah. And then why are 1 and 2 equivalent? Yeah,
Well, if G had a vertex, then it wouldn't be too connected because there would be a vertex cut of size 1. And I mean, if it's connected and you can't disconnect it and moving one vertex, then it must be too connected.
yeah, yeah. So I think these two, we can also see why these are equivalent. Okay, are there questions about those two equivalences? So the next thing that we'll prove is, I guess so this like first theorem we'll prove is like the equivalence of 1 and 3. So that's what we're about to do. So this is a graph having at least 3 vertices, is 2 connected if and only if for each pair of vertices there are internally disjoint paths. Between them. Should I write the definition of internally disjoint paths? Or is it clear? It's just when you have 2 paths and they don't share any vertices except for the 2 that are on the outside. Okay, so let's which direction do you think is easier to prove? The backwards. I have to check because you're like mirror image from what I'm, yeah. So let's prove the backwards direction. So let's assume for every pair of vertices we have internally disjoint paths. Okay, then why are you 2 connected? So let's suppose for all x comma y, there are internally disjoint paths. Yeah,
You have to at least like chop both of them off. So like disconnect the 2 vertices they can survive.
yeah, so like if I delete one vertex, that does not disrupt travel between x and y because I have another way to go. So yeah, so I guess like technically, like what are we proving? We're proving 2 here. So if I have internally disjoint paths between every pair of vertices, obviously you're connected because you have a path between every pair of vertices. And so we're connected. And deleting one vertex does not prevent travel between X and Y because I just always have another option. Okay, so thus we are two connected. Were there questions about that direction? Okay, so for the forwards direction, here's how we're gonna set this up. So let's suppose that G is two connected. Okay, so then we want to show that for every pair of vertices, we have internally disjoint paths. So let's let U and V be vertices in G. And the way that we're going to do this is by induction on the length or on the distance between U and V. So we're going to go by induction on the distance from U to V. Okay, so for the base case, I'm going to consider the case when the distance between the vertices is 1. So how do I find a pair of internally disjoint UV paths in this case?
We have the first path, which obviously is one, then we can connect it to another vertex, X, from X to B. UX B.
So how do you know that that other vertex exists? So we have, okay, so what do we have already? We want to find two internally disjoint paths and we have one automatically, just the edge from U to V. So one path is the edge UV. Okay, what happens if I delete the edge UV? Is the graph still connected? Yeah, why? Yeah, so, okay, so if we delete UV, or I'll just say this. G minus the edge UV is connected. So why is that? Because we know kappa prime of G is greater than or equal to kappa of G, which is 2. Or greater than or equal to 2. Right, so this is by assumption. We assume the graph was 2 connected. And so that means that deleting, if we want to disconnect the graph by deleting edges, we have to delete more than 2. Yeah, you have a
No, I'm just a little confused because we defined two connected with like vertices. So how come now we're putting on edges? Like if we assume that it's two connected, doesn't the distance have to be
Because, okay, yeah, so so we know that the edge connectivity is bigger than the vertex connectivity. Right, so this is saying I have to delete more than 2 edges to disconnect the graph. So that's why if we delete 1 edge, then we're still connected. Yeah, at least 2, yeah. Yeah, 2 or more. Okay, so are we good with this? G minus UV is connected. So that means that there is another path from U to V. And that's automatically going to be internally disjoint from the edge UV. So that proves the base case. So we found 2 internally disjoint paths from U to V. Are there questions? Okay, so now let's do the induction step. So I'm gonna let d u v be equal to k. And suppose, so our inductive assumption is gonna be if the distance between 2 vertices is less than k, then there is internally disjoint paths between those 2 vertices. So I'll write that in parentheses. If d, let's say x, y is less than k, then there exist internally disjoint p paths from x to y. Okay, so I'm gonna let W be the vertex before U on the shortest UV path.
Between,
Yeah, so like, okay, yeah, so here's, if this is my sorry, I wrote this down backwards from how it is in my notes, so I'm just gonna switch it up so that I don't mix up later. Okay, so we have V, W, and then U over here. And then this is like our shortest UV path. Okay, then what can I say about DUW? What is the distance from U to W? Yeah. Yeah, why?
necessary for.
Okay, yeah, so we know that this is a path of length K, right? So this is a path of length K minus 1. Can there be a shorter path from, yeah, no, because if there was a shorter path from U to W, then there would be a shorter path from U to V as well. Okay, so we know that DUW is K minus 1. So then we're going to use the induction hypothesis. So by the induction hypothesis, we have internally disjoint UW paths, P and Q. I guess it could, maybe. Um, so yeah, okay, so let's look at a couple of cases. So, and I'll draw pictures for each one. So one case that you just mentioned is if V is a vertex along P or Q. So then how would our picture look? We have U, W, V, and then we have internally disjoint paths P and Q. So let's say P is the one that includes V. So we have like some path like this. And then another path like this called Q. Okay, so if V is a vertex along P or Q, then how do we get internally disjoint paths from U to V? Yeah,
We have that P and Q together, make a cycle, and so we just split it additively.
yeah, so okay, so if V is a vertex along P or Q, so like in this picture, then we get internally disjoint paths by taking, so in this picture, P minus the edge WV is a path from U to V, and then another one is Q, and then we add in the edge from W to V. So these are internally disjoint paths from U to V. Okay. So that's one case, and then are we good on this case? Okay, so then the other case that could happen is V is not along either of these. So if not, okay, so then how does our picture look in this case? So we have U, W, and V. And we have paths P and Q from U to W that, and they don't include V. So I could just draw them like this. Okay, so our picture is looking something like this. Oh yeah, and we also have an edge from W to V. Okay, so since G is two connected, I can delete any vertex and G is still connected. So the graph G minus W is connected. So that means that there is like another path of travel from V to U that avoids W, right? So there's like some other way to go over here. So since G minus W is two connected, it contains a UV path, and I'll call that R. Okay, so we'll draw R in the picture. So we don't know if it intersects these or not. It could do anything. So this is our R. Okay, now we have two cases. So like our goal still is to try and get internally disjoint paths from V to U. So if R avoids P and Q, then we're good, right? So if R avoids, so it doesn't intersect P or Q, then we have internally disjoint paths, right? From U to V. So for example, that would just be given by R. So in this case, we're assuming it doesn't intersect P and Q. And then we could take either of P or Q together with the edge WV. So maybe I'll say, yeah. So yeah, this is a good observation. So if it avoids P or Q, then we're good. Yeah, because we could have our two internally disjoint paths would be R and whichever of P or Q. So for example, P together with WV. Or just depending on which. Okay, good. Are there questions? Okay, if R shares internal vertices with both, this is kind of the last remaining case. So I'm gonna let, well, yeah, okay, so just intuitively, if we're in this scenario, how would we make internally disjoint paths from V to U using R? Yeah. Yeah, so we could take. So yeah, what am I gonna do after this? Yeah, so we'll do like R until it intersects and then follow that path, and then the other path would be the one down here. Okay, yeah, so that's what we're gonna do, so we'll just set that up. So I'm gonna let Z be the closest vertex. How do I want to phrase this? I'll say like the first intersection with or of R with P or Q. And by first, I mean the closest one to V. Okay, so this is going to be my Z. So without loss of generality, I'm going to assume that Z is on the path P. It could have been Q, but we could just rename them. So without loss of generality, we'll assume that Z is in P. Then the paths Q together with the edge WV and the path following let's see. So yeah, so we'll say the path following P from U to Z. And then following R from Z to V. So these two paths described give us internally disjoint paths from U to V. And that finishes the proof. Okay, are there questions? Okay, so so yeah, so just going back, we were proving where did it go? Oh, we're proving this theorem. So now we've proved the equivalence of 3 and 4 with 1 and 2. So the last one is this ear decomposition thing. So let's see what that is. So I'll make a definition. An ear of a graph G is a path whose internal vertices have degree 2 in G. So for example, let's say this is my graph. Then this is an ear, an example of an ear. And we also want to say, sorry, in addition to this, we want the path to be maximal with that property. So for example, things that are not ears, like this edge by itself is not an ear because while this is a path that automatically satisfies internal vertices have degree 2 because it doesn't have any internal vertices, it's not an ear because there is a larger path containing it that satisfies the conditions. And then like another thing that's not an ear would be something like this because it has an internal vertex with degree 3. Further questions?
Yeah, is this equivalent to just the endpoints having degree not 2?
Yeah, I think so. Yeah. So yeah, so an ear, so yeah, you could also say an ear is a path where the internal vertices have degree 2 and the I guess, okay, the only issue with that is if you're looking at a cycle, I think you would still call like this an ear, even though the endpoints have degree 2.
Where an ear can't be a cycle?
Yeah, because it's a path. Yeah. So I think this situation is the only thing that violates what you said. Yeah, are there other questions? It's always so weird that the wind does that. It sounds like someone's like knocking on the other side. Okay, and then an ear decomposition. Of G is a decomposition P0 up to PK such that so what is this? We're writing G as a union of subgraphs P0 up to PK such that P0 is a cycle and PI is an ear for I going from 1 to K. So for example, this could be our P0. And then we're just meant to start adding ears onto this thing. So this could be P1. P2, and so on. Like that. We'll do another example. So can you, yeah, do you have a question?
Yeah, so when we decompose a graph, are we allowed to use the same vertices in multiple subgraphs in the decomposition?
Yeah, but the edges can only appear in each part once. So as an example, can you all give an ear decomposition of the Peterson graph? So I'll draw this. Okay, did anyone ear decompose the Peterson graph? Yeah, what was your like, can you just say like your strategy?
So I wanted to have
Yeah,
Well, I just like got a point on the star.
yeah,
Up and then to the right. And I did that for every. And then one to the right. And I just did that at every point of the star. I repeated that.
uh-huh.
And the cycle is the star.
And then we have the cycle.
Yep, some of the internal, I mean, all the internal verses have to recreate that.
I'm like, no, I don't know. I'm actually confused now about the definition of an ear because like. Okay, so this is my question. So for example, like this is not so like okay, so if I start with this as my cycle, this is not maximal because I could keep adding edges, right? Like I could there's a longer path, right? But I think that same issue appears here, right? Like why is P1 an ear?
Extend, like, were you trying to extend P2?
I guess I was trying to extend P1.
That well, I think the question is like the internal vertices, is it the internal vertices in G or in the decomposition?
Like in G, P1 is not
Well, also
an
the
ear.
vertex.
P1's on its own in here, right? Like if you took disregard G.
You need G, I know, you need to have degree two in G. Right? Yeah, otherwise you could just take every, yeah.
Maybe there's more to this, like maybe it's like yeah, like okay, so PI is an ear of what? I think it okay, I'm gonna open up the book really quick. I think that this should say like PI is an ear of the graph obtained by unioning everything up to PI. Yes. Okay, so this is so PI is an ear of P0 up to PI. Okay. That subtlety was lost on me the first time I read this. Okay, so does that make sense to everybody? So like, for example, P1 is not an ear of the whole graph. No, wait, it is an ear of, no, okay, now I'm confused again.
It should only has to be an ear of the piece to that point.
Yeah, so why is P1 an ear?
Oh, it's just maximal and not maximum. Like, you can't extend
Yeah,
that any.
if you just consider P0 P1, you can't extend it, and then without P3, P1 has to be.
Why, but why can't I extend it like this?
Because then you put internal verdicts and shit.
Oh, yes, yes, yes. Okay, okay, okay. So we have, right. So if I did that, I would have an internal vertex of degree 3, which is not allowed. Okay. Okay, I think I'm good with this. Is everyone else good?
Here that you can create, it's like.
Yeah, yeah, it's just,
Avoid some of P1, P3, and P2.
yeah. Okay, so, right, so, okay, so like, just to reiterate, like P1 is an ear of P0 union P1. P1 is not an ear of the whole graph, right? Yeah. Okay. So going back to this example, I think we need to change our decomposition a little bit. I think you can pick the cycle to be the same still. I think we just need to do something different for, like, okay, so we have the cycle and then this is P1. And then I think maybe we're good.
Yeah.
If we go around this way, so P2 and so on. Cause like, so if I take the cycle, then I add on this, which is an ear of that. Then I add on this, which is also an ear of that. I keep going around. Okay. So next time we will prove the theorem. We run out of time for today. But like the gist of how this is gonna work is it's like you pick a cycle and then just start adding stuff on to get the decomposition. And there will be, so there's no problems to do tomorrow. There will be one due next Friday, which I'll post in next, like tomorrow or today. And the midterms will be done, I'll be done grading them soon, but it is like, it takes a little bit of time because like you all prove different things, so I have to check if it's true or not. So it's slower than normal midterm grading, but it's very fun.
Anyone like would add something crazy?